I'm Rakshit Agrawal. I'm the Director of Research and Development at Camio, and today I'm going to discuss how containerization unblocks the barriers to fast and easy deployment of AI-driven visual recognition applications. What I mean by this term is that we are talking about AI and how we want to take AI into the real world and how that process can be really complicated, but you can make it simpler by deploying containers in the field. So the topics are sort of laid out in a way that we'll first go over what it means to take research from notebooks all the way to the chipsets ranging across Tesla T4s, ARM processors, so there's a full spectrum and Intel processors all the way, and how actually when we use containers, this deployment to different infrastructures, different architectures actually becomes much more flexible. And also we'll discuss the full AI deployment pipeline from research to end, how Camio works with such a pipeline, and how it adds confidence in the iterations. Because we need continuous iterations as we are improving our solutions, improving our AI models, improving the algorithms. There are so many pieces, and we want to be sort of able to develop it, spend time in development, and then take it all the way to the production side without really too much concern and with confidence. So it all gives us adaptability, speed, and reliability, which is sort of what we are gaining with the help of containers and the orchestration tools around the containers world. And then we'll briefly discuss some trade-offs and limitations that's around this space and how we can basically build a new field where containers are at the center of it, and we can figure out better solutions to unblock all the barriers. So let me start by discussing some vision AI in the real world, what it means. We've all seen data sets like the demo data set on the left, where you have really clear cut faces and you're performing things like face detection on a very simple face. But that's really not what we see in reality. Reality snippets are just a small sample from what our cameras see when they're actually performing real-time AI. And same thing in terms of research, that when we are talking within the research realm, it used to be my task to really just build some solutions for a data set and then perform, get the best metrics for that data set. And it's really, like a small space where the problem is working, and you have to be optimized in that. There's nothing wrong with that part on its own, but that solution is not going to be delivered in isolation. When we deliver it in the real world, we are working with something like real-time video search. So even though an object detection model needs to classify something as vehicle, we actually need to make it a part of a much larger system where you're just searching for the terms and getting those videos like Camio. At the same time, I want to show this direction of what it means to take stuff from research notebooks, where you have the most liberty to practice what you want, try around, play with the data, visualize it, try thousands of models, different hyperparameter settings, and all this research that is really required to build a final solution is best done in an environment which supports research. It may not be ideal to just do it all the way right at the edge. So perform it over there and then take it to the edge where devices are like ARM, small appliances, data centers, large rack servers, where they all have their limitations like low compute, low power. Then we have some consumer grade CPUs and GPUs, so we need to adjust to that. And then you always have larger devices like Xeon processors and NVIDIA RTX or Tesla T4 or RTX 5000. All those higher end categories, they all work very well, but you don't know where your solution is going to run. So you have to sort of make it work every which way while still maintaining research in isolation, right? So how we actually bring all this all the way. So that brings us to the point of what is containerization. Very simply, a container is a package unit of code, dependencies, and environment. What I mean with this is you have code which can run, which needs interpreter or a compiler, and we sort of know how to package that small snippet of code. With Java, we know that we make the binaries. With Python, we know it's interpreted on the fly. But that is just a piece of code. Then it has its dependencies, the libraries. So that's another set, which you know how to package together, or we know how to install it at runtime. And then it's all sitting within large environment. So there's an operating system layer where it's all sitting, right? So there are dependencies corresponding to OS. Containerization says, let me take these three layers all together, your logic, your dependencies, which is the libraries, and the hosting environment, the host OS, package them all together, and deploy, which means if you have a supporting runtime, you just take that container all the way, deploy it. So you ship the image, then the container can be just deployed on a container runtime. And that's it. It has all the resources within itself. It has your code. It has built-in dependencies. The limitations are sort of gone at that point, and you just have to use the right runtime. So that's a very, very quick overview of what containers are. And to make the abstractions clear, I'm using a comparison that Docker provides within virtualization, virtual machines, which are driven by hypervisors, and how Docker is slightly different from them. So in a virtual machine environment, you have infrastructure and a hypervisor. And then each machine is fully isolated. They can only be on the same network, but they are not sharing any OS level resources. Separate kernels, separate code, everything is separate. Whereas in containers, we are trying to use common resources as much as possible. And really the edge, the top end thing is just the application. So you sort of have same hosting layer, which is then running the Docker runtime on it. And then each application is just performing what that application needs to do. And it can use or share OS resources, making it much, much more efficient to run within the same host machine. And the deployment process takes sort of 3 steps. So if you're just working with a Docker file, which is Docker is the popular containerization tool, you would write a spec file, something like on the leftmost, where you're saying, let's start from a Python image, Python 3.8 image, install some of the dependencies and so on, right? So you set all the logic and everything in this file. So your code still stays the way it needs to stay. The spec file is helping build a container. Now, once the image is available, you go on to the second file, which in this case is like a Kubernetes resource definition file. So what this file would do is it will create the deployment spec. So you have an image on the left. Once the image is obtained, you want to tell, given a runtime, deploy it in a certain way. Again, just describe it in the form of a YAML, and finally just deploy it using all the commands on the right side. So this kube control is one of the tools for Kubernetes to deploy it. I switched to the term Kubernetes in the middle, but Kubernetes is another tool, which is the sort of the most famous container orchestration tool, which means it works with containers and builds a cluster which uses containers within it. So I'm not going into too much detail of Kubernetes alone, because containerization and how we use them works very well, but that's another abstraction which we can use. That understanding containers is sufficient because Kubernetes can basically manage everything inside those. So to give an example of what this kind of infrastructure, these containers give us the capability to do, I'm giving an example of an AI pipeline for videos. So this is what Camio does. You connect a gateway device within your local network where the cameras are sitting. So the videos from cameras are going to the gateway device, which is doing some processing to determine what goes into the cloud. And then from the cloud, you have all the data available as real-time video search, analytics, notifications, alerts, everything is available from that point on. So we need to perform several kinds of operations: video operations, data operations, ML operations, right? These are 3 broad categories where everything falls in. So a traditional pipeline would say, at the edge on the gateway device, let's just perform all the video operations, because that's where we have the nonstop real-time stream. Perform some operations on that video, compress it based on motion, etc., and then send everything into the cloud, where you can perform complex data operations as well as ML, because you have Tesla T4s there. You may not have those at the edge. But a hybrid system says, what if I have better infrastructure at the edge? Can I take the same logic and run it on the edge and make it cheaper? I won't have to pay for several instances in the cloud. Actually, you can, because if it's in the form of a container, really it's nothing different than running in the cloud versus running at the edge. You just need to make sure that you have enough physical hardware resources underneath, and then you can run those containers at the edge. And even the containers would tell you whether there's a problem with resources or not. So in terms of new coding, nothing is really required, because your logic, which was still within the form of a container, is now just running at a different location. Let's say you want to do more at the edge because you have a larger device at the edge, or maybe you don't have so many cameras, you can actually do more at the edge. Let's push more at the edge, do very little in the cloud. But if you are in a resource constrained environment where you can really just get a small Raspberry Pi running on solar cells and you do have multiple cameras, maybe very, very few operations at the edge, but those operations are then sending sufficient amount of information to the cloud, and then you are running containers more in the cloud. So wherever compute is required, the blocks can actually move very easily because they are so neatly containerized. And that is the beauty of using something like containers, which gives us this flexibility of moving anything anywhere. So just to give a very quick overview of how it works in action, look at this video where we are performing social distancing and mass detection. And as they're moving on a 3D grid, we are measuring the distances between individuals. At the same time, we are tracking them. We are performing mass detection around their faces. And all these tasks are split into different modules that are working. Now, the same thing can run all the way in the cloud and run much faster on several cameras altogether, but it can also run at the edge, and you will have faster results sort of because in the cloud it's going through a queue and then it's being processed in a certain way. It can still run at the edge. The logic doesn't need to change. It just distribute your code the way you would, convert it into modules, containerize them, and run whatever you want at any location. So to describe the life cycle quickly, what I'm going to say is that when we want to gain confidence in iterations, we need to care about the deployment life cycle, which means there is experimentation and you want to do a lot of experimentation because that's what best solutions are about, right? A lot of experimentation, a lot of research, figuring out what works well. So you have algorithms, models, training, data, everything takes place. And then once you have performed those rounds, you want to develop the solution which will actually work. After doing that, testing and production are two main things. So you want to put it into testing for a certain duration, and then you want to move it to production. Once it is in production, the job is never finished, right? Because you get feedback, you get more real world results, you understand what worked well, what did not, what is it that you can improve. And since it was running, you have more data to improve it. So go back and do this entire cycle again and again. So it is great in terms of development. But what happens is when we enter into such cycles, the time spent is distributed very differently. You end up spending a lot more time on development and testing rather than experimentation, which you really want to do. So the process, which really should flow something like this, where you have data collection, algorithm, inference, executable, so it's basically the process of developing something and distributing it. It has these problem areas which are high risk and low impact, like platform specific packaging, platform specific testing. These areas are the ones which really break the speed. And how we work with them, when we have containers, we actually just convert our logic into containers, and then we let the deployment specs take care of platform specific deployment. And that really controls the way these things are distributed without too much pain and overhead. So just to quickly go over the key takeaways from this process is that adaptability is key. You need to deploy to different infrastructures, different architectures. That is going to change. We have more edge TPUs. We're going to get more neural net specific edge devices. So we want a platform which can, just do the right kind of abstraction of code and then deploy it wherever it is required. And with the same thing, we need speed. We need pipelines for moving top research, state-of-the-art models all the way to the edge, and we want to do them reliably. Containers and the world around containers, which means Kubernetes, orchestration, all the tools that are surrounding that world, mostly supported by CNCF, Cloud Native Collaborative Foundation. Those tools are really adding to this world of adaptability, speed, and reliability. And a quick discussion of trade-offs and limitations, which means first, it's a large paradigm shift, right? So we know that message passing and communications are going to be performed differently. So that's one thing which takes time whenever you're moving from one piece of technology to the other. But hopefully it will just continue to work in a certain way that we all adjust to it. Then there's a problem with large deployments. Sometimes these images, because they are containing everything packaged together, can be pretty large. And if the endpoint is a really low bandwidth region, it may not be able to pull that. So there is work being done in that area, but that's a known limitation right now. And the third one is which is again for now that the lowest compute devices, it still needs something like an ARM processor on a Raspberry Pi to run containers and Kubernetes. We are not sort of at 8-bit processors running all these pieces. So maybe it changes in the future, but that's no limitation for now. So feel free to ask any questions. I'll have my question session now. And even after that, feel free to email any questions to me at rakshit@camio.com. To learn more, just go to camio.com and learn what Camio does in real-time video search. To learn more about containerization and how we use it, go to the following link. And I've also placed a link for Kubernetes here, which is a great place for all the reference around the domain. Thank you so much. Please feel free to ask any questions.